All right, so let's look at a problem like this one. Use a different marker that's not worn out like that one. If 45.5 grams, or moles, let's make it moles because we haven't gotten into the grams to moles conversion yet. Propane 1 all. So we burn 45.5 moles of propane 1 all completely. How much heat energy? Let me finish writing this out and we'll talk about that, okay? How much heat energy will be liberated? What does it mean to be liberated? Freed, okay? So we're freeing the energy. Where did the energy come from if we're freeing it? In the bonds. Okay, chemical reactions store energy where? In the bonds. So the energy, you could think of it in these terms here as being trapped in the bonds, and we're freeing some of it. Okay? Just another way of saying the same stuff you already know.
What is that propane 1?
Propane 1 all. So propane is a hydrocarbon. It has 3 carbons in a chain with a bunch of hydrogen stuck around the outside of it. Propane 1 all also has 3 carbons, but in addition to everything else, it's got an OH group, an alcohol group, an oxygen-hydrogen group stuck on one end. And it says 1 here because it's on one of the end carbons, not the middle carbon. Okay. I know that doesn't mean a thing to you right now, but that's what it means. All right. So now what we need is an equation that shows what the reaction is when we burn propane 1 all. Now later in the semester, you'll be able to make those kind of equations just off your head, out of your head. You won't have to have me show you what the equation is. But right now you have a chart with those equations on it. Now on the test you won't be using that chart, but I will give you the equation. Okay? But if we were using the chart today, we found that the reaction for burning propane 1 all is this. This is the chemical equation rather, not the reaction. So this is propane 1 all, and it's typically a liquid, and we're going to react that with oxygen, and the ratio that gives us a balanced equation is this. And something I said at the beginning of this unit, this is the only kind of equation we'll be using this semester where there are fractions. Everything else after this we'll be using only whole numbers. And that produces then 3 moles of carbon dioxide and 4 moles of water. And then the enthalpy change, which corresponds to the heat liberated. I said corresponds to, doesn't mean it's exactly the same thing. The enthalpy change is what's happening in the system. Is 2,021 kilojoules per mole of propane 1 all. So for every mole of propane 1 all, we get this much energy liberated, that is moved from system to surroundings. Okay? Now, when I write it this way, this is telling me what's going on in the system. Okay? So if you remember this graph, or this graphic, we said in the system, that's for a chemical reaction like this, the system is what's going on in the bonds between the atoms. Okay? So if we're losing energy in the system, the delta H is getting smaller in the bonds. So this side, these bonds over here have more energy stored in them than these bonds. Yes?
I know this is not, it has something to do with about the practice.
Okay, don't go there just yet. Hold that question until I get past this, okay? All right. This system then, if there's less energy at the end, that energy has to go somewhere. And where does it go? Surroundings. So it leaves there and goes, it's got to go somewhere because we can't get rid of energy in the universe, okay? And all together, all this together makes up the universe, okay? So we're having energy leaving the system and going to the surroundings. Got that? And then when we did the graphs where we did the reaction energy diagram, we have energy in the system lowering, so we're starting with higher enthalpy over here and lower enthalpy at the end, and you have an activation energy hill, right? And so what we're looking at here is the amount of energy from here to here. That's our delta H there. Okay, all these things are tied together. Got that? All this has to do with this stuff. Now, but in order to use this equation to help us with our calculation, I've got to have an equation that includes the energy in the equation itself. This is what's happening in the system. We want to know what's happening in the surroundings, and that's what we're going to rewrite this equation to do that. Got that? So this tells you how much energy the system lost. That system energy goes to the surroundings. We have to write an equation that includes the energy as a product that shows what's happening in the surroundings. Y'all follow that? 1, 2, 3, 4? Step by step? Yes, ma'am.
How come you put 9 over 2 instead of 50?
9 over 2 instead of 50?
Yeah, it says plus, and then you put 9 over 2 O2.
Well, because I want to keep this as 1 mole. And that's the way to make the math work out.
No, I'm just asking, how come you put 9 over 2 instead of 50? That's definitely 1 mole.
9 over 2 is not 50. 9 over 2 is 0.45.
I was looking at the regular propane.
Oh, got it. Okay, I got you. You were looking at propane, not propane 1-all. Got it. Okay. All right. And they are different chemicals. All right. So, now then, in order to show this energy in the chemical equation, then I've got to write this into it, and this is what's happening in the system. So if it's losing energy in the system, what's going to be different in the surroundings here? Huh? We'll gain energy in the surroundings, so we'll have plus 2021 kilojoules. That's how you put it in the equation. Okay? The system's losing energy, the surroundings gaining energy. Okay? System's losing energy, surroundings gaining energy. System's losing energy, that's going to the surroundings. All these things are tied together. All talking about the same stuff. Now that we have this, we can use it to do this calculation. So on a test, if you have to do a conversion like this, you must have an equation written out that includes the energy in the equation. Okay? Got that? That's part of your point structure. You lose points if you don't have it. So let's rewrite that. Well, we rewrite the equation. Let's build our calculation now. We've got 45.5 moles of propane 1-all, and we're going to find out how much energy is liberated. So what's our starting amount? 45.15 moles. And that goes over 1. I'm sorry, 45.5. I said 1.5, didn't I? Moles of propane 1-all. I could have written it just like this. Is that a little easier? Let's do that. 45.5 moles C3H7OH. Okay, put that over 1. Okay? Starting amounts always go over 1. Now we need a conversion unit or factor. In the last unit of instruction here, we built units from equality statements, and it was required that you write out the equality statement to justify the unit. Y'all following me there? In the last unit, we wrote convert units from equality statements. It was required that you write the equality statement and then use that to justify writing the conversion unit. Well, what happened to you? You were walking around with just a brace yesterday, and now you're back on crutches.
Yeah, you told me to walk with crutch so I can get it today.
Okay, well, here's what I need you to do, okay? I need you to put your name over the top of this in pen and stick that in your file, okay? Will you do that for me? Now you can move if you want to, since you don't crush it again. You want to do that?
Yeah.
All right. All right. Now that we have the energy in the equation, this is justifying the fact that for every 1 mole of this, I'm getting this much energy. That's our justification. This over here, we've got an implied 1 coefficient here. This number has a coefficient, and this one has a coefficient. So the coefficient here is 1. We just don't write 1s like we don't write 1s for 1x or 1y in algebra. But there's a 1 there, and we can say these are moles. This is 1 mole of this, and 9/2 moles of oxygen, and 3 moles of carbon dioxide, and 4 moles of oxygen. So we got 1 mole of propane 1-all, so we can put that on the bottom. Why did I put it on the bottom? Yeah, the starting amounts on the top here has moles of propane 1-all, so we want that to be on the bottom here, so that eventually we end up canceling that. Our conversion factor then takes the ratio of this to this, and this part goes on the top because we're trying to find how much heat energy. And heat energy is measured in kilojoules, or any joules. Kilojoules just means 1,000 times a joule. Okay? So we get 2,021 kilojoules of energy out of this. Okay? Huh? Well, I did put per mole. When I put it over 1 mole, that's per mole. It's a different way of writing the same thing. So this number right up here, the delta H is negative 2,021 kilojoules per mole. Well, per mole of what? Remember, we said I did that little example where I asked if you wanted 100. Then after everybody raised their hand and said they wanted 100, I said kicks upside the head. So a number without the units don't tell you anything. Well, units without a number don't tell you much either. Moles of what? Well, sorry, in this case, it's moles of a substance. We need a species. Well, the what part is the propane 1-all. Okay? Well, we put it in the equation, and this is this many kilojoules per 1 mole of this. It also happens to be the number of kilojoules for 9/2 moles of oxygen, or for 3 moles of carbon dioxide produced, and 4 moles of water produced. Those ratios apply to all of those. Got that? All right, now back down to here. We need to simplify. How do we simplify? Cancel out our units, and we can cancel our species just like those x's and y's in algebra. Okay? And then we're going to do the math. And everybody's allowed to use a calculator. In fact, you need to bring your calculator on Monday. Okay? Bring your calculator. Everybody hear me? So 45.5 times 2,021 will give me 91,955.5, and the units I have left are kilojoules. Okay, and that's our initial answer. Now that we've got our mathematical answer, we need to check for significant digits. We need to look at all the measured or calculated numbers in the problem. This is a measure. Well, actually, this is actually calculated. There's a calculated number. There's a calculated number. Somebody's done the math for us and found that number. Of those two numbers, we need to choose the one that has the least digits. 3 in this one. 4 here, 3 here. This has the least digits here. So this is the one we're going to use to figure out how many significant digits we're going to end up with in our final answer. Okay? We want to have the same number of significant digits. So we're going to underline all the insignificant digits. So we count from the left. You find the first non-zero digit. That'll be your first significant digit. 1, 2, 3. Those are our significant digits. Everything else gets underlined because we're going to get rid of those eventually. Alright? Now we can't just write 919. That's 100 times smaller than we need it to be. Okay? We just want to round off those 5s. What we need to do is to write it in scientific notation. Now, mathematically, 919 times 10 squared would be fine, but that's not what you're allowed to do in a chemistry class. In a math class, in a science class, you must write your answer in scientific notation if you're removing a number from the ones place. Okay? In a science class, in this class in particular, you must write your answer in scientific notation if you have to get rid of a number like this 5 here in the ones place. So to work that out, then we need to move our decimal place to between the first and second significant digit. The first significant digit is the first non-zero digit from the left. That would be this one right here, going from the left to the right. That's our first non-zero digit. So this and this are the first two significant digits. We're going to move our decimal place between those two. 1, 2, 3, 4 places. 1, 2, 3, 4 places. Now, the underlining is required. The little bump here is not required. If you can do that in your head, it's okay. But the underlining is required. This arrow showing that we're rounding off is required. If you don't show me the arrow, that's a point. Okay? An easy point. Show the arrow. Okay? Then we're going to write 9.19. Oh, but this 9's got to be rounded up because this is a 5 or greater. Alright, so the 5 makes the 9 round up to a 10. Carry that 1 to here. That makes that a 2. So we're not going to write 9.19. We're going to write 9.20. Huh? Yeah, because that digit right there is significant. And we're replacing it with a 0 because we're rounding up 1, right? Yes? That zero is required. It's significant. Okay? Times 10 to the, this 4 here makes a 4 here in the exponent position. So that 4 goes right there. And then we have kilojoules as our unit of measurement. Alright? How are we doing? Yes?
So, will you put like practice worksheets or anything on this stuff?
Email a practice test.